All right, we're going to talk about parallelograms. Let's spell it correctly first. Parallel. There's two L's and one L. That's parallel. And then ogram. All right, like ogram. I know it is, but I just did that just to, I know it's one word, but I just put it in here just to help you spell. It's a gram, G-R-A-M. Okay, my letters look weird. Sorry. I apologize. Goodness. So my handwriting is not the best in the world. G-R-A-M. How's that? Is that better? Alright. Let's talk about what a parallelogram is. Alright. This whole chapter, we're basically concentrating, taking a look. Yeah, we're concentrating on four-sided figures. So in general, what's a four-sided figure? Quadrilateral. It's a quadrilateral. Okay, quad. It's a four-sided figure, and this whole chapter is talking about different types of quadrilaterals. Okay, so a parallelogram is just one type of quadrilateral that we're going to deal with. We're going to deal with several other different types of quadrilaterals, but a parallelogram is one of them, and it's a pretty important one. Okay, it really is. So let's draw a parallelogram. They usually, now that technically is a parallelogram, but they usually make it look like this when they draw parallelograms. Yeah, they kind of slant it a little bit. Okay, that's your average, normal, everyday parallelogram. Okay. Now they can look different than that, but that's what they usually use to show what a parallelogram is. Now, in that word parallelogram, I'll tell you what, let's scooch it down. It was up there, wasn't it? Yeah. In that word parallelogram, obviously, what's the main geometry word that's in that word? Parallel. Okay. So parallel. Okay. And so that means something about this is parallel, doesn't it? Okay. Well, what do you think? Yeah, these two line segments up top here. Yeah, the sides opposite. Very good. Okay. The sides opposite each other, like this one and this one. Let's call this A, B, C, D. So the sides opposite each other are parallel to each other. Okay, that's the definition of parallelogram. They would be. So both pairs of opposite sides, okay, both pairs of opposite sides are parallel to each other. That is the definition of parallelogram. Okay, we're going to learn some other things about a parallelogram, but the first thing that we're going to learn is by definition. Let's jot these down. Okay, so number one, by definition, actually I got some little black line in there. Let's scooch that down. Yeah, there we go. It must be some kind of a border for something. I'm not really sure, but yeah, every once in a while you're right. See, it's like right in there. I think it's in the program somehow. There must be some kind of I don't know, but yeah. So, but the definition says what? That both, let's write it out, both pairs of what? Opposite sides are parallel. And I'll just put the parallel symbol. Is that all right? Okay, both pairs. Now, we're going to deal with something later on in another lesson where only one pair is parallel and the other pair is not parallel. That would not be a parallelogram. Okay, so to be a parallelogram, both pairs of opposite sides have to be parallel. Yep.
Does that mean for all the both pair of opposite sides are equal to?
Well, not just because they're parallel doesn't always mean they're equal to each other. All right.
One was a little bit longer. The top end was a little bit longer than the side two would be.
Right, then this one wouldn't be. You're exactly right. And so it is true, you're jumping ahead a little bit, but that's okay. But it's a good question. It is true that the opposite sides are equal to each other, but not by the definition. Okay. Right now we're just sticking with the definition for right now. Is that all right?
Yeah.
But we do have some theorems. And the rest of these, I believe the rest of them are theorems. Yeah, I don't think any of these are postulates. Let me just take a quick look. Yeah. Nope. Nope. So both pairs of opposite sides are parallel to each other. Let's do the second thing, and these are all theorems. And I'll do this in another color. So just like Alex said, he saw this and he said, hey, both both opposite sides have to be equal to each other, because if I took this side right here, and if I extend it out, made it a little bit longer, what's it going to do to this side? It's going to make it so it's not parallel to this side. Would you agree? So these would have to be equal to each other in order for these other two sides to be parallel to each other. Because if they weren't equal, if this was just a little bit longer, then this would come out like here. Everybody understand that? Okay, and then so this right side will not be parallel to this left side anymore. So you're absolutely right that the opposite sides must be parallel to each other. So those two are also parallel. Not parallel. Yes, equal, congruent. Okay, both pairs of opposite sides are also equal to each other. It's not by the definition, but it's just a theorem. Okay, a theorem tells us this. So let's say this. Let's say that both pairs of opposite sides are what? Equal. Or you could say congruent, whatever. You okay with that? All right, let's see what else we might be able to say about this. We'll go in order according to how they do this. And let's do this in another color. Let's go orange. All right, let's see the third theorem. Okay, well, it's not the third theorem. It's the second theorem, but it's the third thing that we're talking about as far as parallelograms. The third thing is the angles. Let's take a look at these angles. Look at this angle right here. What do you think might be true here? It's equal to b. That's right, okay, that the opposite angles are equal. Let's maybe figure out why. Well, first of all, we're going to talk about this in a second. I'm trying to think why here. Okay, we do have two parallel lines cut by transversal, but that means this and this one would be what to each other? Supplementary. Right, not complementary, but supplementary. Why? Because they're consecutive interior angles. Remember that one? Or same side interior angles. Same side interior angles are complementary. Do you agree? So look at this. So these two add up to 180. Agreed? So let's just put a number in here. What does this look like? Maybe about, probably looks closer to about 70 degrees. We'll say it's about 70. All right? So what would this angle have to be then? Have to be 110. Would you agree? All right, so let's watch this. Does it make sense? Because parallel lines, these two are parallel lines. This would be your transversal right here. And then these are same side interior angles, or consecutive interior angles, what we call them. And so if this was 70, that would have to be 110. Yes, because consecutive interior angles are supplementary when you have parallel lines, right? And that's something that we've learned before. So if you're going to do this in a proof and have a reason, you would say that these two are supplementary because they're consecutive interior angles, right? If two parallel lines are cut by transversal, then the consecutive interior angles are supplementary. That was a mouthful, but you understood what I said, right? Because we had a whole chapter on that kind of stuff. So if this is 70, this is 110. Let's go back to this one right here. We can't really directly say, okay, if this is 70, this is 70, but we can kind of do it indirectly. If this is 70, this has to be 110. If this is 110, tell me what this is going to have to be. That's right, because look, now I have these two parallel lines cut by AB, which is a transversal. Do you agree? So I've got two parallel lines cut by transversal. These are also consecutive interior angles. So if this is 110, this has to be what? It's got to be 70. Everybody see that? Let's keep going. If this is 70, what's this have to be? 110. So what does that say about our pairs of opposite angles? That's right. So we could say that both pairs of opposite angles this time, not sides, but angles, are also equal to each other. And it's a theorem, and we basically just proved the theorem, didn't we? We just kind of did it, right? We used stuff that we knew before about consecutive interior angles, and we went through, stuck numbers in there, and we said, hey, they must be equal to each other. Now, was 70 like a magic number that would only work if this was 70? Of course not. It would work with any angles, okay? Everybody okay with that? So that was kind of interesting. That was kind of nice to see why they are equal to each other. So we know that the opposite angles are equal to each other on a parallelogram. All right. Let's put number 4 down. Here's another theorem. Now, it kind of deals with what we just dealt with. All right, deals what we dealt with. Look at this. we call these, let's see how they say it. Yep, the consecutive angles. All right, the angles right next to each other. So the 70 and this 110. What must be true about the consecutive angles of a parallelogram? They're supplementary. So let's write that down. That the consecutive, I'll just shorten that, consecutive angles are supplementary. When I say consecutive angles, it means the angles that are right next to each other. Everybody see that? So the 70 and the 110, they're supplementary. And look, this 70 is next to this 110 as well, isn't it? And they're supplementary as well. I mean, take a look at all the way around, right? These two are supplementary, these two are supplementary, these two are supplementary. You got it? So the opposite angles are equal. The consecutive angles, the angles that are next to each other, basically, are supplementary. They add up to 180. We getting it? Yeah, not so hard. And I believe, yeah, there's one more, but I'm going to do another picture for this. Let's go back to the white color. And let's do that original picture that I drew. And we'll make it look like this. So watch this thing. If this is a parallelogram, okay, so if it's a parallelogram, I'll put, by definition, this would be true, wouldn't it? Plus all that other stuff would be true. By definition, this is now a parallelogram. Watch this. If I have just one angle given on a parallelogram, what do you think you can say this parallelogram is? It's got to be a rectangle. Why? What do we know about a rectangle? A rectangle is what? Well, actually, we haven't even said the word rectangle yet, have we? Yeah, I was getting a little ahead of myself. But if this is a right angle, what are all the other angles? They have to be right angles. So let's give some good reasons. Why is this one up top here a right angle?
Because they add up to 180.
Because consecutive, let's say it how the little theorem said it. Because consecutive angles are supplementary, okay? Now, we could find this angle two different ways, couldn't we? We could say, well, it's supplementary to this one because they're consecutive angles. Or we could say what? Both pairs of opposite angles are equal. So if this is 90, then this has to be 90 for two different reasons, right? All right. So that's got to be 90. What's this have to be down here? It's got to be 90 as well. Does it make sense? And we do know that's a rectangle, don't we? All right, but we haven't officially said rectangle just yet. But just to think ahead a little bit, what do you think a rectangle is then? A rectangle is also a parallelogram. A parallelogram, right? Make sense? We can't say a rectangle is a square because this is a rectangle, isn't it? But it's not a square. Would you agree? All right. And we'll talk more about that a little bit later. Yes. Yeah. Every square is a rectangle, but not every rectangle is a square. Exactly. But every square and every rectangle is a what? Parallelogram. You got it. Okay. On quadrilateral, right. All these things are all quadrilaterals. Alrighty. Let's see. Where do I want to go from here? We got another couple other theorems here. This is good stuff. Let's copy that. And let's make another parallelogram. Even though that technically is a parallelogram, let's make one that we normally see. We normally see it slanted like this, okay? It's just kind of their favorite parallelogram to draw, so that's what we're going to do. We good? Now what I'm going to do, thank you. Now what I'm going to do is draw a diagonal. Remember we talked, was it yesterday we talked about diagonals? I think it was. Where's a diagonal drawn from? From any vertex to the what? We didn't say opposite yesterday. Okay, give me a nice good word. Very good. To a non-consecutive vertex, we'll say. All right, to a non-consecutive vertex. So we've got this situation right here. Let's actually draw both of them. I'm going to change colors. I'm going to say, did I do the right? I think that's just highlighting that. Let's change that to yellow. And let's make another one and make it blue. Okay. Now we're going to talk about the, and we might as well label our vertices here. Call this ABCD again. Sorry for my lack of creativity. Alright, so ABCD. Let me just make sure, say this right, good. Okay. Look at these two diagonals. Does it look necessarily like the diagonals are equal to each other? They are?
No.
I'll tell you
I
what.
don't think they do.
Tell you what. Let's copy and paste this one. All right, and yeah, let's just rotate it so it looks a little bit. Let's do that. Let's do this. Tell me if that's flat. Well, I see a little. It's not going to go completely flat, but you get the idea, okay? So there's that one. Let's do the yellow one. And ooh,
No.
yeah. So it's a little bit of what do you call it? Optical illusion. Yeah. But look at that. We'll make that pretty flat. Yeah, they're definitely not equal to each other. Would you agree?
Oh my god.
Okay. It looked a lot closer up here, didn't it, than it does down here. And all I did was copy and paste it. So, and I just rotated. I didn't change the lengths of it or anything. Okay. So they're not equal to each other, but they do something else. What do you think? Without looking at the book, what do you think? We'll put a point right here, and we'll call that P. Or what equal?
Are their angles equal?
BPC? You talking about an angle?
Yeah.
Yeah, I'm not talking about the angles, though. You're absolutely right. These vertical angles would be equal to each other. Absolutely right. What about the sides, though? The diagonals themselves. Alex, what do you think?
Is AP equal to PC?
Absolutely is. Okay? So AP would equal PC. All right? Let's just see if it really does. It does, yeah. Well, it's not really a proof. It's a demonstration. It's more of a demonstration. Let's hope. Okay, so I'm going to, right? Do you agree with that? All right, so that's the length of AP. Let's just pick it up. I'm not going to copy and paste. I'm just going to pick it up and put it right here. And look at that. Yep. It's the same, isn't it? So guess what P is then? It's the midpoint. Yeah, it's the midpoint. Or we could say this. We could say that DB, line segment DB, does what to line segment AC? It bisects, right. So we say that the other diagonal bisects this diagonal. What do you think might be true about the other one? The yellow one. Okay. So we're saying those are probably going to be equal to each other, right? So again, let's just see if it is. We'll keep it in red. So if I go to here, right? Do you agree? It's pretty close to DP, right? If I take this and I pick it up, again, it's not really a proof. It's just kind of demonstrating. All right, actually, let's kind of move this down here. All right, now, and then look at that. It's right on, isn't it? So would you agree? Yeah, so it is being bisected. Okay, so what we say, this is a theorem, and the theorem says that diagonals of a parallelogram. Oh, I didn't show you the symbol for parallelogram yet. What do you think it looks like? What do you think it looks like? A parallelogram. How about that? Isn't that amazing? So it kind of looks like that. It's kind of like a slanted. I didn't do that very well, but you get the idea. Okay. So diagonal of a parallelogram. It's supposed to look like a miniature version of this parallelogram. All right. So the diagonals of a parallelogram, they do what? They're not equal to each other. We showed that earlier. They bisect each other. That's right. They bisect each other. So P is the midpoint not just of AC. P is also the midpoint of what else? DB. All right? That's very helpful. All right? Because, of course, you see what they're going to do, right? They're going to give you the lengths of sides. You've got to figure out what the lengths of sides are. In fact, they're not just going to give you just regular numbers. What do you think they're going to throw in here? Like variables and things like that. They'll put like a 3x plus 2, right? You got to set them equal, or you got to make one twice as big as the other, or something like that, okay? Does that make sense? You've seen it before, right? It's really, we are not really doing much new stuff as far as the math is involved. The math pretty much stays the same all year long. It's just the pictures and the shapes that we use just change, okay? And we just learn different stuff about those shapes, but the math really stays the same. That's what's kind of nice about geometry, is the math doesn't get much harder. It's just a matter of knowing what equals what and all that good stuff, all right? Let's take another look. Look, I've marked all that stuff, and somebody said something about vertical angles, right? That was Caitlin? All right. What else do you think you might be able to say, not about the sides or the angles, but there's triangles in there as well, aren't there? What do you think you might be able to say about this triangle APD and this triangle over here, CPD? They're congruent to each other. Give me a reason why this triangle is congruent to this triangle. Side, angle, side. Good. Side, angle, side. Side, angle, side. Agreed? Okay, very nice. What else do you think? Is that the only triangles in there? Yeah, look at this. Yep, this, I'll tell you what, let's go different color here. Instead of marking like 2, 3, 4 arcs, let's just go colors. Is that all right? So the purple one and the purple one. Sorry. I just picked a different, it does kind of look, it looks different on the computer screen. Up there it probably looks a little closer. But look, what about this top one and this bottom one right here? They're congruent because of side, angle, side as well. All right, now if the triangles are congruent, the corresponding parts must be what? Congruent, must be equal to each other. So let's try to find some equal angles in here. So for instance, would you say green? So let's say this angle right here. What do you think in this triangle right here? What do you think this is equal to over here?
C.
Yeah. No, it's not C. Because how do you know? How do you know? Because look what it's opposite. Well, look what it's opposite. Don't just look at it as it's flipped or twisted, because sometimes that's too hard to see. The easiest way to see which angle it is over here is you look to see what side it's opposite. It's opposite the one with one arc, or with one tick mark. You see that? So you come over here, here's one tick mark. Which angle is opposite the one with one tick mark? It's PBC. It's that one right there. So those two are equal to each other. Why would those two be equal to each other? Because you proved the triangle is congruent, and these are equal because of CPCTC. Corresponding parts of congruent triangles are congruent, right? So look, if this one and this one are equal, then this one and this one are equal. Two different reasons. You could say, let's see, you could say alternate interior angles, couldn't you? Right? Parallel lines cut by transversal, right? Alternate interior angles are equal. You could say these triangles are congruent, or actually you don't even need to know those triangles are congruent. If this angle is and this angle are equal to this one and this one, the third angles are equal because of the third angle theorem. Okay? All right? Is it coming to you now? Look at this. What about this angle right here? What's that equal to?
Angle C.
Well, you can't just say angle C. DCP, right. So it would be this one right here. And again, several different reasons. They're corresponding parts of these two congruent triangles, or you could say that they're alternate interior angles, right? All kinds of, all that stuff that we learned before all comes flooding back though, doesn't it? All right, isn't that nice you learned all that stuff? Yeah, there you go. And of course, we'll just put 3 here. That angle right here is equal to this angle down here. Got it? Does that mean that these two angles are necessarily equal to each other?
No.
No. So when we say they bisect each other, they don't bisect the angles though, do they? Everybody see that? So this angle right here is not equal to this angle right here. We will talk about something at another point where it's not just an ordinary parallelogram, but we will talk about something where the angles are bisected. But they're not bisected on a regular, everyday parallelogram. Okay? Make sense? The only thing that's bisected are the diagonals. All right, let's see what else. I think we've covered everything, I believe. Let me just double check. There's an example. There's an example on page 401, but I'll let you peruse that yourself. Okay? All right, so you can look at that yourself, because it looks like you guys are ready to go now anyway. So let me give you some work to do. You have an extra day to get your homework done. So let me write down your assignments. It's page 403. Page 403, and it's section 6.2. Page 403, numbers, it's go 9 to 12, and then you're going to go 15 to 20. There it is, right there. That's it. Alright, 9 to 12, 15 to 20. Alright, have a good long weekend. See you Tuesday, right? Okay.